In this video, we're going to continue to explore the quaternions. And just as a reminder of what we did in the previous two videos, in 14a, we set up the complex numbers, and then in part 14b, we set up the quaternions. And our strategy was to take the real numbers to be fundamental, the most fundamental objects. And what we did is we formed the complex numbers by taking ordered pairs of real numbers, and we formed the quaternions by taking ordered quadruples of the real numbers. That is, the complex numbers were R2, and the quaternions were R4. And that's what I have written here. For example, we would say A is a complex number because it's formed by an ordered pair of two real numbers. And we went back and forth between this notation 1, 2, and the more common notation 1 plus 2i. And for the quaternions, let's say we had some quaternion B, which is formed by an ordered quadruple of real numbers, 1, 2, 3, 4. And we went back and forth between this ordered quadruple notation and the scalar vector notation. That is 1, 2, 3, 4 could be represented as a scalar part, 1, plus a vector part, which is represented as 2i plus 3j plus 4k. And we based our formulas for complex number addition and complex number multiplication on real number arithmetic. What we said is that complex number multiplication satisfies the following formula, which we talked about in part 14a, and quaternion multiplication follows the following formula, also called the Hamilton product. And this is a little bit complicated. It involves multiple combinations of the elements in the two quaternions. In this video, we're going to develop a new interpretation of the quaternions, thinking of them as ordered pairs of complex numbers instead of ordered quadruples of real numbers. And we're going to find that these representations are pretty much the same, or they're going to be isomorphic. Here's essentially what we're going to do. Let's suppose we have some quaternion Q, which is 1, 2, 3, 4. What we have been doing is interpreting this as a quadruple of the real numbers 1, 2, 3, 4 in that order, or 1 plus I plus 2j plus 3k. What we're now going to do is consolidate some of these pairs. That is, instead of interpreting this as 1, 2, 3, 4, the real numbers, we're going to interpret it as the pairing of two complex numbers. We're going to interpret it as a pairing of 1 plus 2i and 3 plus 4i. So we're going to pair these two complex numbers together into an ordered pair and call that a quaternion. Now this is a slightly different interpretation, and this is what we're going to explore in this video. Let's begin this interpretation by studying the three imaginary quaternion units first. That is, we had the multiplicative identity 1, which is just given by 1, 0, 0, 0. We had our first imaginary unit, which I'm going to call capital I, or big I in this video, just to prevent it being confused with little I, which is going to be the complex number I. And this big I could be represented as 0, 1, 0, 0. That was the first imaginary unit. The second imaginary unit is j, which is going to be 0, 0, 1, 0. And then k, which is going to be 0, 0, 0, 1. Now, if we change our interpretation here, instead of interpreting all of these as quadruples, we interpret it as two complex numbers, the pairing of complex numbers, the multiplicative identity is going to be read off in the following way. We look at the first two units. This is 1 plus 0i, so 1 is going to go there. Then we have 0 plus 0i, so in the second component we're going to have 0 there. So now the multiplicative identity, interpreted as a pairing of complex numbers, is just going to be 1, 0. Now the first imaginary unit, big I, we read this off. We read off the first pair. This is going to be 0 plus little I, and then 0 plus 0i. So big I, the quaternionic I, is going to be the pairing of the complex number little I with 0. And then we repeat the following procedure for j and k. J is going to be 0 plus 0i, that goes in the first component, and then 1, 0, that's going to be 1 plus 0i. So big J, the quaternionic J, is going to be 0, 1. And then finally we have k, which is going to be the pairing of 0, little I. So this is a slightly different interpretation, and we're going to find that doing this is going to be completely consistent with the quadruples. But what we have to make sure is that the multiplication definition for the pairings preserves the following formula, which is what sets up quaternionic algebra. That I squared, j squared, k squared, and ijk are all equal to the negative of the multiplicative identity. Let's now formalize what we've been talking about. So we're going to define the set H, the set of quaternions, as C times C, or C squared, just the ordered pair between complex numbers. So some quaternion, let's say Q, is going to be written as the ordered pair AB, where A and B are both just some complex numbers. Now we're going to proceed in a normal way. We're going to, after having defined the set that we're talking about, we're going to say what we mean by addition and multiplication between two quaternions. And we're going to give a description of quaternionic addition and quaternionic multiplication in terms of complex number operations. So let's begin with quaternion addition. And this is actually quite simple. So if we had two quaternions, let's say Q1 and Q2, Q1 is going to be the pairing between A and B, and Q2 is going to be the pairing between C and D. And we're going to define the quaternionic addition in the following way. Q1 plus Q2 is going to be given by A plus C, B plus D. Just your normal vector addition. You add component-wise. Just to give an example of that, let's say Q1 is equal to the pairing 1 plus 2i and 3 plus 4i. And we had Q2, which is the pairing between 3i and 1 plus I. We just add component-wise. So we get 1 plus 2i plus 3i. That gives me 1 plus 5i in the first component. And then I add 3 plus 4i and 1 plus I. That gives me 4 plus 5i in the second component. And that's all there is to it for quaternionic addition. And notice this is identical to interpreting Q1 not as the pairing between 1 plus 2i and 3 plus 4i, but instead as 1, 2, 3, 4. And interpreting Q2 not as 3i, 1 plus I, but as 0, 3. 0, 3 because there's 0 in the real component there. So 0, 3, and then 1, 1. So here we have 0, 3, 1, 1. And then we just add component-wise. And we get the same thing. We just get 1, 5, 4, 5. Or in our complex number pairing way, we get 1 plus 5i, 4 plus 5i. As before, quaternion multiplication is going to be a little bit more complicated than addition, but it's still quite manageable if we interpret it in these pairings of complex numbers. So we're going to define the Hamilton product in the following way. If we have two quaternions, let's say Q1, Q2, Q1 is going to be given by AB, Q2 is going to be given by CD. The product, Q1 times Q2, is going to be given by the following formula. The new first component is going to be AC minus BD bar, and the new second component is going to be AD plus BC bar. And this goes back to what I was saying before. We're defining quaternion multiplication in terms of operations upon complex numbers. That is, this product between, let's say, A and C is complex number multiplication. And this bar over the D here and the bar over the C here just represents complex number conjugation. So we're defining quaternionic operations in terms of complex number operations. And you can also notice that this formula is extremely similar, if not identical, to the formula for complex number multiplication. If A, B, and C, D were just two complex numbers, this would be pretty much the same formula. We'd have AC minus BD in the new first component, and then we'd have AD plus BC in the new second component. It's just that here we have this D conjugate here and the C conjugate here, and these are placed there just to make the formula work out with what we've been dealing with the quadruples. Now let's check to make sure that we can recover this important formula for quaternionic algebra. So we're going to start by just checking to see whether I squared is equal to minus 1. So we have I, or I should say big I, which is going to be the pairing between little I and 0. And I'm just going to square it. I have I0 times I0. Now if I work through the formula for quaternion multiplication, I have I times I minus 0 times 0 bar, which is going to give me I squared. And I have I times 0 plus 0 times I bar, which is going to give me 0. And then I squared is just minus 1, so I indeed get minus 1, 0. And I encourage you to check that j squared also squares to minus 1. And now let's check to make sure that ijk also gives me minus 1. So I have big I, which is again little I 0. I have j, which is 0, 1. And then I have k, which is 0, little I. And then quaternion multiplication is associative, so let's multiply the first two first. Working through the formula, I have I times 0 minus 0 times 1 bar, which will give me 0. And then I have I times 1 plus 0 times 0 bar, which leaves me with I. And then you notice already that ij is equal to k. I multiplied I0 by 0, 1, and I get 0i, which is indeed k. And then you can check for yourself that when you square k, you will also get minus 1. So this formula does indeed work out. Now let's try a more complicated example. Let's suppose I have q1, which is I1, which in the quadruple fashion can be interpreted as 0, 1, 1, 0, and q2, which is going to be 2 plus I, which can be interpreted as 2, 1, 0, 1. Now we're going to calculate q1 times q2 in two different ways. Actually, I'm going to compute it in the paired way, and then I'll leave the computation in the quadruple way for you as an exercise. So q1, q2 is going to be just this, and now let's work through the formula. So I'm going to have I times 2 plus I minus 1 times I bar. Now the conjugate of I is minus I, so I'm going to be left with I times 2 plus I plus I. So that's the first component. Now the second component is going to be I times I, or I squared, plus 1 times the conjugate of 2 plus I, which is going to be 2 minus I. So the new second component is going to be I squared plus 2 minus I. And then you do a bit of simplification in the components, and writing them in a plus bi form, you get minus 1 plus 3i, 1 minus I, which in quadruple form is going to be minus 1, 3, 1, minus 1. And I encourage you to check as an exercise, multiply these two quaternions, 0, 1, 1, 0, and 2, 1, 0, 1, and you should find that you get exactly the same thing. Now that we've done a couple examples of quaternion multiplication interpreted as ordered pairs, let's now talk about the conjugate of these new quaternions. So what we want out of the conjugate, q bar, let's say I have some quaternion q, it's going to be given by AB, and the conjugate, q bar, is going to be given by CD. What I want is that when I multiply AB by CD, that's going to give me A bar plus B bar in the first component, and then the second component drops to 0. And this is because the conjugate is always set up to give squared lengths of the thing that you started with. So essentially what I have to do is I'm looking for what C and what D are going to work here. So I'm just going to multiply AB by CD and set it equal to A bar plus B bar, 0. So let me just work through the formula. I have A times C, and then I'm going to have minus B D bar. So let's focus on that AC part first. So I have the A already there. So it seems pretty natural to let that C be equal to A bar. And that's indeed what we're going to do. We're going to have C be equal to A bar. And then I have minus B D bar is going to be equal to B bar. So how is that going to work out? So we're going to have to let D be equal to minus B. And if you write that out, just to make sure that the conjugations all work out, that is the correct guess. So that's going to take care of that first component. And then if you write it out, you take care of the second component is already taken care of. We're going to have A times minus B. So it's going to be minus AB. Then we're going to have plus B A double conjugate, which is going to be plus BA. So those two are going to exactly cancel to give me 0. So this is going to turn out to be the correct guess for the conjugate. So the conjugate of Q, which is given by AB, Q bar is going to be given by A conjugate negative B. And let's work through this just to see why it makes sense. For example, if I have Q be equal to 2, 3 plus 2i, Q bar is going to be given by 2. We're going to take the conjugate of that first component. The conjugate of 2 is just 2, so it's unchanged. And then I'm going to negate the second component. That's going to become minus 3 plus 2i. And if you work through the multiplication here, you multiply either Q times Q bar or Q bar times Q, you're going to find that you're going to get 17, 0, which is actually the sum of squares of the components here. That's going to be 2 squared plus 3 squared plus 4 plus 2 squared, which is going to be 17. Now this formula for Q bar actually makes a lot of sense if we think back to quadruples. Let's go back to this Q here. And now if we think of this as a quadruple, this is going to be 2, 0, 3, 2. Now how do we take the conjugate of a quadruple? We just take the last 3 components, which are going to be the I, J, and K components, and we just negate all 3 of those. So when we do that, we're going to have that 2 being the same, negative 0 or 0, then minus 3, minus 2, which is exactly the same as what we got for Q bar. And in general, the conjugate of A, B, C, D is going to be A minus B minus C minus D. And now if you think of those in pairs, now the first 2 are going to be now, instead of A plus B, it's going to be A minus B. So that's why it's just the conjugate. It's just negating the second component of that first pair. And then both components of the second pair are being negated. So it's the complete negative, not just a conjugate. It's the negation of that second pair. So this actually makes a lot of sense if you write out going back and forth between the pairs and the quadruple interpretations. What makes this interpretation of the quaternions as ordered pairs of complex numbers really interesting is that I'm going to now show you how you can find a nice quaternionic representation in terms of 2x2 complex valued matrices. And this is in contrast with the representation I gave you in the last video as 4x4 real matrices. So now let's suppose I have 2 quaternions, Q1, Q2. Again, Q1 is going to be AB, and Q2 is going to be CD. And then when I multiply the 2, I should get AC minus BD bar, AD plus BC bar. And now I'm going to essentially guess. I could just tell you what the matrix representation is going to be, but let's sort of guess at what it's going to have to be. So the main insight is going to be that it's going to be a 2x2 complex valued matrix. And the main guess I'm going to make is that the form of the matrix is going to be such that if I have some quaternion AB, I can just plop A and B into the first row of its corresponding matrix. So I have some quaternion Q1 AB, I could just plop A and B into that first row there, and same thing with CD, I could just plop into that first row. And now if the form of these matrices is going to be consistent, I'm going to plop the first 2 components of the answer, Q1 times Q2, into this matrix as well. So now I have 2 of the 4 values of the matrix already covered, I guess. So now I'm looking for these remaining 2 entries here. So now notice in terms of matrix multiplication, I'm going to have to multiply A times C plus B times the entry down here, and that's going to have to give me AC minus BD bar. Now that A times C part looks pretty good already, and then I'm going to have to get B times this entry here, let's call it X, has got to give me minus B D bar. So what should that value down there be? It should be minus D bar. And then I'm going to use the same argument for what the entry down here should be. So I'm going to have A times D plus B times something, which is going to give me AD plus B C bar. And again, here the AD looks pretty good. Then I have the B times that something down here has got to give me B C bar. So it's pretty obvious that that thing down there should be C bar. So this is going to indicate already the form that these quaternion matrices are going to take on. So when I have some quaternion, let's say CD, I'm going to plop the C and D into the first row. The 2-2 position is going to be the conjugate of C, and then the 2-1 position is going to be the negative conjugate of D. And then just to keep the forms consistent, I'm going to use that same pattern for this quaternion down here. So I'm going to have A, B, minus B bar, A bar. And then if you work through the matrix multiplication here, you're going to get the following things down here. And now let's sort of see that all these matrices have the same form. In the first row, I have the answer. I have the first component of the new quaternion, and the second component of the new quaternion. And then down here in 2-1 position, I should have the negative conjugate of whatever's up here. And if you look at it, I have that sign flip there. And if I take the conjugate of AD plus BC bar, you will get precisely the B, A, and the D all have the conjugate over them. And that double conjugate with C cancels. And then I should have down here, what I should have is a conjugate of what's up here in the 1-1 position. And again, if you just take the conjugate, you'll see that you get precisely this. The A, C, and B up here don't have the conjugate over them, so they're going to have the conjugate over them. And the D is going to have 2 conjugates over, and that's going to cancel. So the forms of these matrices are going to be in the following way. The quaternion, the matrix representation for the quaternion AB is going to be given by A, B, minus B bar, A bar. For example, if I had this quaternion 1 plus I, 2 minus 3I, I plop the 2 components in the first row there, just 1 plus I, 2 minus 3I. Down here in the 2-1 position, I'm going to have the negative conjugate of what's up here. Now the negative conjugate is going to just negate the real part. So the negated real part is just going to give me minus 2 minus 3I for the 2-1 position. And then for the 2-2 position, I just take the conjugate of what's up here in the 1-1 position, which is going to be 1 minus I. And I claim this is the matrix representation for this quaternion. Now let's go back to our quaternionic imaginary units, big I, big J, and big K, and look at their 2x2 complex matrices. So the multiplicative identity, 1, is going to be given by 1, 0. Big I is going to be given by little I, 0. J is going to be 0, 1. Then K is going to be 0, little I. And then we just use our discovery in the previous slide of what the matrix representation is going to be. The multiplicative identity, 1, is going to be precisely the 2x2 identity matrix. Again, because I have 1, 0, I just plop it into the first row, 1, 0. In the 2-1 position, I have the negative conjugate of whatever's up here, so 0. Then down here in the 2-2 position, I have the conjugate of what's up there, so that's 1. So that's pretty nice already that I get the identity matrix. Now for big I, which is going to be little I, 0, again, I just plop it into the first row. Down here in the 2-1 position, I take the negative conjugate of 0, that gives me 0. And then down here in the 2-2 position, I take the conjugate of I, which is minus I. And now this is going to be the 2x2 matrix corresponding to big I, the quaternionic I. And now for J, I have 0, 1. That's going to be in the first row there. In the 2-1 position, I take the negative conjugate. That's going to be minus 1 down there. Then I'm going to have 0 down here. So that's your 2x2 matrix for J. Then K, you just repeat the same thing. Put the 0, 1 in the first row. I have the negative conjugate down here, which is just I. Then the conjugate of 0, which is 0. And that's going to be your 2x2 matrix for K. And now you can check for yourself that if you square I or J or K, you'll get the negative identity matrix. And furthermore, if you multiply I and J in that order, you'll get K. If you multiply J and K, you'll get I. And if you multiply K by I, you'll get J, just like you would normally with quaternionic multiplication, this time in terms of matrices. Let me make a few last observations on these 2x2 complex matrices. Let's take some plain old quaternion, Q, which is going to be AB minus B bar, A bar. Now let's take a look at the determinant of that matrix. So that's going to be given by A times A bar minus B bar, B, which is going to be equal to this, A bar plus B bar. Now what is that expression? That would be the squared length of the quaternion Q. Now that's a really nice property because when we set up complex numbers as 2x2 real matrices, that's also what we saw. That when we take the determinant of that matrix, we get the squared length of the thing that we're trying to represent. So that's a pretty nice observation there. And now one other thing that I'd like to point out, and this is going to be really interesting for those of you who are into physics, especially quantum mechanics, is that let's say I have Q again, I have the matrix representation, and the question I'd like to ask is there some operation which when applied to this matrix will give me the matrix representation of the conjugate of Q? And it turns out that this operation is called the conjugate transpose. And it's exactly what it sounds like. If I start with Q, to get the matrix representation of Q bar, I'm going to take the complex conjugate of all the values in this matrix and then take the transpose. And now let me show you how that plays out. So these entries on the main diagonal, when I take the transpose, aren't going to change their position. And then I take the conjugate, so I get A bar, that's A bar there. Then I get A double bar there, that's going to give me A. And then the negative B bar is going to go up here. And then I take the conjugate, it's going to give me just plain old minus B. And this B down here, the B up here in the 1, 2 position is going to move down here. And then when I take the conjugate, it's going to be B bar. And this is going to be represented as Q dagger. The dagger represents the conjugate transpose. Now let's take a look at the form of this matrix. So up here in the first row, that is the quaternion, that is the matrix representation of the quaternion A bar minus B, which is precisely the conjugate of Q. And notice this has the same form too. I have A bar minus B. Over here in the 2, 1 position, I have the negative conjugate of what's up there. And then over here in the 2, 2 position, I have the conjugate of what's up here in the 1, 1 position. So taking the conjugate transpose will give the matrix representation of the conjugate of Q. And now one is often interested in matrices which have the property of being what's called unitary, which is that when I multiply Q by Q dagger, I get the identity matrix. So if a matrix has this property that Q times Q dagger is equal to the identity matrix, it's said to be a unitary matrix. And now let me do precisely that. I'm going to multiply Q by Q dagger. I'm going to set it equal to the identity matrix. So I do the matrix multiplication. I find that A times A bar plus B times B bar has got to be equal to 1. And what does that mean? That when this expression here is equal to 1, that means it's a unit quaternion. So the take-home message here is that any unit quaternion represented as a matrix is a unitary matrix. At a more abstract level, if I take all these unit quaternions, I take their matrix representation as a 2x2 complex valued matrix, and I give them the group operation of matrix multiplication, that group is essentially what's called the special unitary group, SU2. And this notation SU2 means that the 2 means that we're talking about 2x2 complex valued matrices, which have 2 properties. The U means that these matrices are unitary, which means they have that property, that Q dagger is equal to 1. And the special means that they have a determinant equal to 1. And this group, SU2, is pretty much the unit quaternions. It's all the matrices of this form, which also have unit length. All these quaternions which have unit length are pretty much SU2. So that's probably the nicest thing about considering quaternions as 2x2 complex matrices. And that wraps up this video. Hopefully you've enjoyed that discussion of quaternions, and stay tuned for more videos. Thanks for watching.